Okay, so now we'll apply the boundary conditions and get the solution to this thing. So these are our two boundary conditions. The derivative of the z velocity in the r direction will go to 0 at r equals 0. This is the center of the pipe, so this is the symmetry condition, the same kind of condition we saw really get flow between the plates. For flow to be symmetric, it's going to have this condition essentially. Well, it's actually possible for it to have two different situations. It could also have a point of some kind. So if you imagine the profile is like this, of course the velocity in the radial direction would be 0. It could also be symmetric and have some weird velocity, look something like this. But anyway, that's not what the velocity looks like, so we don't really have to consider that. So anyway, we're going to go with this symmetry condition, and then Vz will go to 0 at r equals 0, of course, because that's the no-slip condition at the pipe wall. So if we look at our profile here that we've got to solve for two undetermined constants. We'll apply this one first. So dVz dr is equal to gr over 2 mu plus c1 over r. And this has to go to 0 at r equals 0. So that's going to zero out the first term. And the second term would go to c1 over 0, which of course would go to infinity, unless c1 equals 0. So in order for this condition to be satisfied, c1 has to be 0. We update our solution. We get that Vz is equal to gr squared over 4 mu plus c1, which is now 0, plus c2. So that's our updated solution. Very simple. Now we'll apply our second boundary condition. Second boundary condition is that Vz goes to 0 at r equals r naught. So Vz is equal to 0 at r equal to r naught. And so Vz at r equals r naught, plugging that in, gives you g r naught squared over 4 mu plus c2. We set that equal to 0. G r naught squared over 4 mu plus c2, and solve for c2. We get c2 is equal to negative g r naught squared over 4 mu. Okay, so now we update our solution again. So we have Vz, which is a function of the radius. The radial coordinate is g over 4 mu times r squared minus r naught squared. So that's our, r naught squared. So that's our solution for the velocity. And we also know that dp dz is equal to g. So that's our pressure gradient. So pressure gradient of g gives you a velocity profile that looks like this. Parabolic profile, once again, in the radial direction for velocity.